This is a lesson on the spring force, commonly known as Hooke's law in force analysis. The spring force starts with the idea of elasticity, and that's the concepts where materials can be deformed, and when they're deformed, they will exert reaction forces, restoring them to some sort of original geometry. And these reaction forces depend not only on the composition or strength of the material, but also how far the object has been displaced from the original geometry. This could be in 1 dimension of a length, 2 dimensions of an area, or 3 dimensions of a volume. And specifically, if we look at 1 dimension in length, a linear sort of force, we get to the example of a spring. And a spring then exerts an opposing or restorative force in response to an applied force that compresses or stretches the spring from an original length. Again, this is a linear displacement, and we're going to be dealing with linear forces. And the assumption also is that the springs in problems are ideal. In real life, springs aren't ideal, and they may not exert the same force over the entire displacement. And it could be due to deformation, that they're stretched too far, or that they're hot or cold, and that would change how they exert a force. And none of that will be going on. We'll just have an ideal spring. The direction of the spring force may be intuitive based on the concept of elasticity. It'll be a force that restores the spring to its original shape. In order to do that, we need to identify what the original shape was, and this has to do with identifying an equilibrium position, or where the relaxed length L0 is. So if I draw a picture of that, I'll draw a spring, and there's the end of it, and therefore this is the end of the spring, and in this, we can call this delta x is 0 displacement, or just x equals 0 is fine. I think of it in terms of displacement, so I will put a delta there. You may not see that in all textbooks. The spring force restores to the original length. So if I think about a situation where I stretch the spring out and the coils become farther apart and I stretch the spring out, all right, I've displaced the spring a distance delta x away from the original length. All right, and the original length is defined as this. Here's L naught. This new length is L. That's the new length. So delta x will equal L minus L naught. And you can see that it gives this remainder here. Okay, so if I stretch the spring out, it will exert a restoring force. So notice that delta x is in the positive direction, delta x, and the spring force will restore it to the original length, which means that the spring force opposes that. And so that may be intuitive to you. If I push on it, and let me draw that situation down here, I'll mush the spring so that its relaxed length is longer than this length. So this is the new L. We can see that the delta x is in the negative direction here, delta x. And that would assume that this is the positive x direction. Delta x is in the negative direction. And the force that the spring applies, well, the spring doesn't want to be compressed. It will exert a restoring force in the other direction. And notice that these two also oppose one another. These oppose one another, and these oppose one another. So when you think about the direction of the friction of the spring force, think about the displacement, but also you have this intuitive, it wants to be restored to its original length and will push or pull in that direction. And when we're doing this, make sure you're assigning a coordinate system. The positive or negative sign of a force or a vector in a coordinate system comes from the direction of positive or negative in that coordinate system. And I say this because the magnitude of the spring force comes from the vector definition. Here's the vector relationship between that displacement vector and the spring force. Notice there's a negative sign, which I had been suggesting that these two oppose one another. And that's where it comes into the equation, is that these two oppose one another in direction, but they're equivalent proportionally, right? There's this constant in here. And what we call this is the spring constant. The spring constant describes how strong or weak the spring is. So the stronger the spring, the larger the spring constant. So if you push on a spring a distance x and it has some spring constant, you will be able to determine the force on it. In calculations and free body diagrams, I use the magnitude of the spring force, just K delta X. And I don't worry about the vector equation, because when I draw the free body diagram, whatever's going on, I draw the direction of a spring force, and the positive or negative sign won't come from this equation. It'll come from the fact that I've defined positive or negative by a coordinate system. And then I can set it equal to K delta X in the equations. So we have the direction and we have the magnitude. I've picked a couple of questions for us to work through in order to practice applying the concepts. The first question is spring on surface. The problem says a mass of 5 kilograms is attached to the end of a spring which is secured to a wall. Okay, this coefficient of static friction between the mass and the surface is 0.281. Okay, so we have a mass on a spring that's secured to a wall. So let me draw that over here. I'll draw that over here. And I'll have the mass extending this way. And here's the spring. We can draw it like that. There's the spring. And there's the mass attached to the spring. And it's telling me that there's a coefficient of static friction. So I'll put mu s down here and just kind of shade my surface so I know that there's friction down there. And I can write this out over here. M equals 5 kilograms, and the coefficient of static friction, mu s, equals 0.281. I'm going to anticipate having to calculate a friction force somehow, and because they give me the maximum static, or they give me the coefficient of static friction, that suggests to me that I may be calculating the maximum static frictional force. Remember, it's less than or equal to up to a point until it's the maximum value, and then it's mu s times the normal force. And I'll write N here for normal force. Okay, so that's just applying what I know conceptually. If they're mentioning static friction, I know that there's an equation, and I can think about the quantities that I need to use that equation. Okay, I don't have a free body diagram yet, and I really don't know any more details of the problem, so let's keep solving. It says when the mass is displaced 12 centimeters from equilibrium, oh, that's something that I would need to know, is delta x equals 0.12 meters. I'm going to convert that to from centimeters to meters, because that's SI. If I'm using kilograms, the SI value is meters, so I'll convert that to meters. The friction force with the floor just barely keeps the mass from moving. That's, again, to me, the signal that I will be at a critical point where I want to use the max static frictional force, where it says it just barely keeps the mass from moving. And I'm also going to note from that tells me something about the acceleration. It keeps the mass from moving. The mass is not moving, and if the mass is not moving, that means that it has zero acceleration. It says it's not moving relative to the floor. Determine the spring constant. So I don't know K. K, I don't know. And K is buried in my spring equation over here, the force of spring. Okay, so I kind of wrote out what I know. I still need to do a free body diagram. Let's orient this 12 centimeters into the problem. And what I noticed when I first read it is it doesn't say whether it's stretched or compressed. So I'm going to say maybe let's compress it so that here's delta x equals 0, and that it's compressed a delta x in this direction. And you may be able to intuit from this will be a compressed spring, and so that the spring will be pushing back. So when I draw the mass over here, okay, And I don't know if it's compressed or stretched. I'm just picking one, and then I'm going to do a comparison in a second. So if the spring is pushing on it, I can go like this, F spring. And so also I know if it's at rest, there's also friction. And if the spring is in this direction, then the frictional force has to be in the other direction. And this is a static. And it is also the max value in this situation. I can't always assume it's the maximum value, but I will in this situation because it says it's just barely. It's at this critical point. Okay, so that's the free body diagram if it had been compressed. If it had been stretched, the force of the spring would be in the other direction, and the force of the friction would also be switched. It can do that. Then the spring would be stretched out, the spring would be pulling it back, and then the friction can oppose it in the other direction. So it doesn't matter whether it's stretched or compressed in this situation, but it may in other situations because it changed the direction of that spring force. And it changed the direction of the friction force. So if you had other forces going on, that would need to be considered. Okay. We do have other forces going on in the vertical direction. They don't contribute to the horizontal, but we need to remember to write them down. There is a normal force, which I'm going to need because I have a static frictional force, a maximum. I need the normal force. And I can do an analysis in the y direction. I'm going to go ahead and do that. The sum of forces in the y direction equals MAY. There's no motion in the y direction either, so I can write 0 here. In the y direction, over on this side goes all the forces on your free body diagram in the y direction. I can assign a coordinate system here. I will go a standard up and right as positive y and x. So when I write this equation out, I get a positive n minus w. And I see that the normal force is equal to the weight, and I know weight can be calculated by mg. I know the mass, and I know gravity, and so that can be used in this equation where I see n. Okay, so I've done the vertical direction. Let's move to the horizontal direction because we're trying to find the spring constant, and the spring constant is buried in the spring force, which is in the horizontal direction. So let's set up the equation. The sum of forces in the x direction equals max. Well, we know the acceleration in the x direction. They told us it's sitting still, so this has to be 0. Over on this side goes all of the forces on the free body diagram in the x direction. In the x direction, I have a positive force of friction, static max. And then in the other direction, I have the force of the spring. And what's this telling us in the equation is something we kind of already knew, right? Is that these two forces have to balance each other out to result in 0 acceleration so that they're equal in magnitude to each other. And I'm going to write that down. This becomes mu s times mg. Remember the static frictional force is mu s times the normal force, so I can plug that in. And the spring force, I'm going to write in what spring force is. It's K delta x. And again, like I mentioned before, I'm not putting a negative sign in here from the vector equation because I've already taken into account which direction it's in. If I put a negative sign in here again, it'd be accounting for it twice, and I don't want to do that. So we're solving for the spring constant, so I'm going to put the spring constant on one side and everything else on the other. Mu s mg divided by the displacement. And now I can plug in values. Mu s is 0.281, m is 5, g is 9.8, and I can divide that by the length and the displacement in meters. Again, because all of these are in meters, this has to be in meters as well. And when you calculate this, when you run it through your calculator, you get 114.742. The units on spring constant is newtons per meter. That's the proper units, the SI units for spring force. And it makes sense when I go up here. If I have newtons per meter and I multiply by a meter, I'm left with newtons, and that's the units for a spring force. You can simplify this. It rounds to 115 newtons per meter, and that would be the answer for this question. I've chosen a second question, and it is a spring force in a vertical situation rather than a horizontal one. Often they will have vertical spring force situations. So I wanted to do an example for this too. And you can go back to setting up vertical force analysis in a prior lesson that I had on vertical acceleration. The problem says a spring, K equals 830 newtons per meter. Okay, so we're given K, is hanging from the ceiling of an elevator, and a 5 kilogram object is attached to the lower end. Okay, so let me write down K here, 830 newtons per meter. And then I'm also getting a picture in my head that I'm going to write out over here about there's an elevator and there's a spring in an elevator, okay, and it's hanging from the ceiling, and there's a mass on the lower end. Okay, so there's a general sketch of the situation. This is not a free body diagram, this is just the sketch. Okay, so I'm getting an idea of what's going on. There's no supportive surface under the mass. I don't know anything about acceleration yet, but I can read more into the problem to see what's going on. By how much is the spring stretched relative to its unstrained length when the elevator is stationary? Okay, so for part A, that answers my question. The acceleration is 0. Up or down, it's 0. Okay, and we're asked to find the displacement, which is in the spring force. So we're going to have to set up a force analysis in order to get at that displacement and do a force analysis. In this situation, I don't know what other forces are acting on the elevator, so it doesn't make sense to do a free body diagram of the elevator in order to find the spring force. What makes sense to me is that the spring is also acting on the mass, so I can draw a free body diagram of that mass, and I'll draw it over here as a free body. I'm going to note that the spring force is the force supporting the mass upward. And because it is a mass, it will have a weight, and the weight is downward. I'm also going to assign a coordinate system while I'm here. I have no preference. Initially, it's acceleration equals 0. I'm going to note in the second part it says accelerating upward, so I'm going to make upward positive just to make it easy for problem solving. Okay, so positive is upward. And that's it for forces. I have 2 forces, and they're only vertical. I don't have any horizontal forces, so I feel ready to set up the Newton's second law equation that says the net force in the y direction has to equal ma in the y direction. I know this whole term is going to be 0 because there's no acceleration. In the y direction, I write the forces on the free body diagram. I have a positive force of the spring, and then I have a negative weight. I know the expression for the weight. I know the expression for the spring force. Spring force is K delta X. And I'm asked to find the displacement. So let's write out some of the details of these quantities. If I move weight over to the other side and say it equals mg, I can get this equality, and I'll solve for delta X equals mg divided by K. Oh, well, I can calculate this. M is 5, G is 9.8, and K is 830. So when you run this through your calculator, you get the displacement to be 0.0590 meters. Or you can alternatively, depending on where you're giving your answer, it could be 5.9 centimeters. So that's how far that spring gets stretched out if the mass is just put on it. There's a second part of this problem. It says, by how much does the spring stretch relative to its unstrained length when the elevator is accelerating upward at 0.6 meters per second squared? Okay, so in this situation, we have an acceleration upward at 0.6 meters per second squared up. Okay, so I can draw that up in my diagram. That would make sense up here, acceleration upward. And I feel ready with all the information I already have here. I haven't introduced any forces. All I've done is said now it's moving upward rather than sitting still. So when I set up Newton's second law, sum of forces equals MA. Well, MA has a value now. It won't be 0 over on this side. Over on this side goes the forces on the free body diagram in the y direction, and again, it's just the spring force upward minus the weight downward. We're asked to find the displacement in this situation, which is kind of buried in the spring force. So I'm going to move the weight over to the other side and have spring force over on this side equals MA minus plus the weight. I'm going to note that the weight equals mg, so over on this side I get MA plus mg, the spring force. Well, if I simplify, the spring force is K delta x, and that will equal, I'll factor an m out of this side, A plus g. To solve for the displacement, I get delta x equals m A plus g over the spring constant. And I can plug in what I know. I get 5 times 0.6 plus 9.8 divided by the spring constant, which is still 830. When I run this through my calculator, you get a value of 0.06265 meters, which is about 6.3 centimeters. And I'm going to note that this makes sense. It should be larger than when it's just sitting still. And the equation also sort of conceptually tells me that. When I look at this equation here, it says the spring force equals the weight plus a term due to the acceleration. And when I think about it, if it's moving upward, that spring force upward has to not only overcome the weight force, which was what we did in the original problem, the spring force overcomes the weight force as well as gives the object some acceleration upward. So it's giving this, it's overcoming this, and it's giving it some acceleration, so it will be stretched further than when it's just sitting still.